So this lecture is going to look at the idea of torque and rotational equilibrium. So up to this point, we discussed the idea that we can have forces acting on something, and if we sum up the action of all of those forces, if all of the forces cancel out in some way, then that means the sum of the forces would be equal to 0, and we would have translational equilibrium. That is, the object might be moving at a constant velocity, but it's not accelerating in any direction. So, for example, I stand here on the floor, and gravity's pulling me down. The normal force of the floor is pushing me up, and so those two forces are acting to cancel each other out. I'm not accelerating up or down. I'm moving with a constant velocity of 0 meters per second as I stand here. Now, what we can do is we can say, hey, we can constrain our system in some way. We can say this system cannot move freely around. There's going to be some point of it that's fixed about which it's going to rotate. And so in doing that, we say, okay, this system here is going to have a pivot point. So even though there's weights pulling down on this piece of wood, then this part here is going to be fixed regardless. So we introduce a pivot point. And then we note that, well, depending on how far away we are from this pivot point, it's going to determine exactly how strong a force will act to cause this thing to rotate. Now, as we look at this thing here, there's two ways it can rotate. It can begin trying to rotate clockwise, or it can begin rotating counterclockwise. This weight here is trying to make it rotate clockwise. This weight over here is trying to also make it rotate counterclockwise. We'll discuss in a second, of course, the piece of wood also has mass that's causing it to try to rotate one way or the other. We'll ignore that for a second. Now, in order to quantify how strongly a force will act to cause something to rotate, we define a term called a torque. And torque is just how far is the force acting from the pivot point? That far, to this place. What amount of force is being acted? Well, in this case, the amount of force is just the weight of this chunk of metal. What relative direction is it between going from the pivot point out to here and the direction this is pointed? Now, in this case, this relative angle is 90 degrees, and so in a lot of calculations we'll do, this part just simplifies to be 1 because it's sine at 90 degrees. However, it turns out that depending on how you push or pull affects how strongly you will cause something to try to rotate. So in this case, this thing, by pulling straight down, gives the maximum torque it can to try to make this thing rotate. But if I were to put a little string on here and pull to the side with the same amount of force as the weight of this, then I would not be causing as strong a torque, because it would not be, it would be at some other angle than 90 degrees, and thus the amount of torque would be less. Now, if we could simplify this bar that's holding these weights and just say it's like a zero mass bar, then all we have to care about is what does the torque do to the mass over on this side, and what does the torque do to the mass over on that side. But unfortunately, in any real thing we set up, we can't ignore the fact that the object that we hang these things on also has mass. Now, there's two ways we could go about talking about the contribution to the possible rotation of this system from the mass of this bar. We could either measure the entire mass of the bar, calculate the percentage of the mass that's on this side, and then say, okay, this mass that's on this side is trying to make the system rotate clockwise. And then this percentage of the mass over here is acting to make it rotate counterclockwise. So we'd have to count up, how much of the bar is on each side of this, and then calculate from there. It turns out there's a much simpler way to be able to take the contribution of the entire bar as a single number. If we looked at all the mass of the entire bar, we can come up with a quantity called the center of mass. Basically just the average location of the mass of the bar. So here's a little bit of mass, and here's a little bit of mass, and here's a little bit of mass, all the different bits of wood that make up the entire ruler here. On average, the location of all that mass is somewhere right here, roughly the center. Now, it's not going to be perfectly at the 50 centimeter mark. There's always going to be some little variations there. Just in the wood, some pieces have, broken off and rounded off, and maybe there's some different densities and whatnot. But for this, approximately the center of the exact center here will be where the center of mass is. So this location that we call the center of mass will be where we say the entire mass of the wood is located. So there's mass on this side, try to make it rotate this way. There's mass on this side, try to make it rotate this way. But what we can do is we can say the net contribution of the wood to the rotation of the system is that the mass of this bar is basically can be considered to be located at a point right here at the center of the bar, and the entire mass of the bar overall is trying to make the system rotate this way. Okay? So then what we want to do is we want to use the expression for torque and the expression for rotational equilibrium, which the thing is in, and come up with an expression to say, maybe I wanted to adjust the location of some of these things. Like I wanted to be able to move this out a bit, so I need to know how much further I need to move that out. Or maybe I want to hang a different weight here. So can I relate these distances from the pivot point to the amounts of mass? All right. So first thing we'll do is we'll try to move this out of the way without it flipping over on me. Later on, if you hear a crash sound, it's because this thing came out of equilibrium and fell over. Like, oh. Yeah, just get it. Disassemble. All right. So, this quantity, called this torque here, it is a vector quantity, but the direction of it is such that if some forces are acting to try to make the system rotate clockwise, then the vector direction is going to be into, like if this is our clock face, then the vector actually points into the board. And for this, with these trying to make this rotate counterclockwise, then the vector direction is out of the board. So torque is a vector, but the direction that the actual vector points is perpendicular to what directions those forces and what directions the links are going in. So we look at this and we say, okay, to keep things simple, we're going to sum up all of the torques that are making this try to rotate clockwise and all the torques that are trying to make it rotate counterclockwise. So from this expression here, we say that the torques clockwise equal the torques counterclockwise. So, what would be this torque clockwise? Well, since I have mass 1 on right here, it's some distance away. For simplicity, I'm just going to call that, since this is mass 1, I'm just going to say this distance here was R1. So, M1, R1. Now, we got these 2 points. This one here is the actual hanging mass. This one here is the center of mass of location of where we're saying the entire bar might as well have been a mass located at this point. So, since this is indicated by center of mass, we might just hang it. Too far into the video to restart. Just to be to fix what I wrote originally over here, this is the amount of mass, but it's not the amount of force that's being exerted. Because the amount of force, right, in these instances is the force due to gravity, which is going to be the mass of an object times the acceleration. So that means the original clockwise torque over here would have been that distance R1 and then M1 times G. And now we have our full expression. And then we go to these different ones. So R at the center of mass times the mass of the bar that was holding it times g. And because this is another torque acting in the same direction, R2. Now you can see in this case, or with goofing up, was in this instance there's a G on every turn because every source of force in this problem that's trying to cause this thing to rotate is just a weight. And so we could drop off all these G's and now we would have a nice compact little expression for whichever quantity we wanted to vary. So that is, if I vary any of the masses relative to what they were originally, I could calculate new masses or new positions that would be necessary in order for me to still have that beam set up, be able to balance. Now, just to show a few more things related to this, because we have to understand, again, that what is being balanced in this case is the weight that's trying to make something rotate clockwise and the weight that's trying to make it rotate counterclockwise. So I don't have to have a hanging weight in order for me still to have a system in equilibrium. So first off, I can take this stick here, right, and just on its own, I can find some equilibrium point where, in this case, there's mass on the left and mass on the right that's trying to make the system rotate to the left, and the corresponding amount of mass on the other side is trying to make it, rotate the other way. Now, again, instead of trying to talk about the fraction of the mass on this side that's trying to make it rotate like this, and the fraction of the mass on this side that's trying to make it rotate like this, it's easier just to say, well, the entire mass of this thing is just located at a point we'll call the center of mass, which is effectively at its center for a nice uniform object like this. So because the location of the center of mass is at the pivot point, that means if we were to use this formula up here, that means the distance from the center of mass or to the pivot point would be 0, so the net torque would be 0, and so as we see, the object doesn't really fall one way or the other as long as I'm on the actual center of mass. Even without another weight to counterbalance something, or another hanging weight, the mass of this and where its center of mass is still affects our system. So for example, if I put a weight on one side, little finger thing again, basically, you can see that I still have some balancing going on, only now I had to put more of the mass of the stick on the one side to counterbalance this. So we could either look at this system as this amount of mass and this amount of mass trying to make this thing rotate this way, and this amount of mass trying to make this rotate this way, or we could think of this system in terms of this amount of mass is located this distance from the center, and the center of mass of this object is located, somewhere over here. And so there's this mass of the object trying to make the whole system rotate this way, this mass trying to make it rotate this way. Two different ways of thinking about the problem setup. Both would give identical answers, as long as we follow through all the mathematics.